Welcome everyone to the June 2025 UK Freshwater Quality Research Programme webinar. For those new to the series, we are a whole programme of research projects funded by NERC and DEFRA, where we're looking to really strengthen our understanding of the sources and behaviour of pollutants within river systems, understand how the pollutants are changing and accumulating, and what their kind of impact is on the ecosystem and how mixtures of these chemicals impact the ecosystem. And ultimately, we want to kind of influence change. So we want to reduce pollutant loading, inform policy, and inform improvements to the ecological status of UK rivers. Next slide, Finn. So in the programme, we currently have 5 really fantastic projects, and we've been hearing from each of these projects in the webinar series, along with a set of other presentations from international and national speakers. And the purpose of the webinars really is to keep everyone up to date with all the kind of new ideas and new thinking and progress with the projects in the programme, but the wider freshwater quality agenda as well, and trying to build that broad understanding across our communities of researchers, policymakers, practitioners, and other interested parties. So today we're going to hear from the LTLS-FE project. Next slide, please, Finn. But if you do want to get a bit more information about the programme itself, there's a website and a QR code on screen for that website at the minute, but you can join the mailing list or get colleagues to join the mailing list to get all the updates to webinars. There's an email address as well for us as a programme level, so you can contact us about any queries or questions that you've got or points you want to raise. There's also a QR code on the left of the screen, which is about biosecurity e-training, and that's really helpful. That's come about in one of our previous webinars, whereby anybody who's sampling and working in freshwater should really be alert to biosecurity, and we encourage you to take that training as well. So just before we launch into today's presentation, some upcoming webinars. So in July, we were just confirming the exact timing, but we've got a presentation on AMR and bacterial diversity in swimmers, which is a very sort of topical area. So we're going to look at that in July, and then we'll have a break over the summer, but then in September we'll come back. And there's a really early start to this one because the presenter's based in New Zealand, so it's actually going to be at 8 p.m. presentation for them, or a 9 a.m. start for us. But this is a really important presentation about work they've been doing on water quality monitoring that fits policy objectives and drives policy objectives. So that's really important for us to hear some international examples. And then in October, we've got something about landscape and water connectivity in a changing climate and water quality from Julia Knapp. So that's what's coming up. But today we have Theo Jackson from Rothamsted, William Perry from Cardiff, and Mark Rhodes Smith from UK Centre for Ecology and Hydrology, who are going to tell us about the LTLS-FE project and the updates on that. So I think I'm handing over now to Mark.
Well, thank you very much, Joe, for that for those words of introduction. So yes, I'm Mark Rhodes Smith from UKCEH, and together with colleagues Theo and Will from Rothamsted and Cardiff respectively, we'll be giving you a bit of a taste of some of the work we've been involved in this LTLS-FE project. We're all early career researchers involved in different parts of the project. So what are we talking about today? Well, first, I'm going to give a very brief introduction to the research project, a little overview. We've talked in a lot more detail at some of the previous webinars. So today, just the key bits that you need to know to get oriented for then the meat of this presentation, which will be 3 short talks about different components of our modelling framework to try to understand the future of our freshwater ecosystems. I'll be talking about the wastewater treatment and discharge system. Then I'll hand over to Theo, who'll be talking about developments in the agricultural modelling part of the process. And then finally, we'll hand over to Will, who'll be taking the outputs of all of our different bits of works and synthesising them together to understand the impacts on ecosystems. And then I'll wrap up at the end, talking about just summarising what we've said and where we're going over the next 6 months or so. So what is the LTLS-FE project? Very briefly, this is a modelling project where we're trying to understand the future of freshwater health under different climate and socio-economic scenarios for the whole of the UK. That includes Northern Ireland, and it includes a few bits of the Republic of Ireland which drain into Northern Ireland. The whole country is represented on a 5-kilometre grid, and we'll be running this model from 1980 to 2080. So we have a little bit of observed at the beginning, and then about 60 years of futures hereafter. At the end of the project, we will of course be publishing various results, but we'll also be publishing a lot of the data sets that we produce and even the code. So if big slabs of Fortran are your cup of tea, you'll be able to play around with the model and run your own scenarios. If you're not so keen on big slabs of Fortran, we'll also be providing web tools to help you explore the different scenarios and the results of our models. What are we modelling? Well, there are something like 100 different variables we'll be producing by the end of the project. These have been selected in consultation with stakeholders in the first few months of the project, and it'll include water quantity, so flows and stores across the country, loads of different chemicals in the freshwater environment, and that's going to include macronutrients like carbon, nitrogen and phosphorus, a set of 7 or 8 metals, some critical industrial chemicals, pharmaceuticals and personal care products, things like caffeine and cetirizine, pesticides, which Theo will be talking about later, and polycyclic aromatic hydrocarbons, particularly those involved in runoff from roads. I think I can also say that we've recently agreed to add in a couple of extras in collaboration with the Pacific Project, a couple of extra antibiotics that may be of particular interest in the future. We'll also have the physical properties of the rivers, so things like the water temperature, the pH, and other such variables. And then we'll also be then producing indicators for the impact on the ecology. That'll be the abundance and richness of different taxa, and popular indices that give you some indication of the health of the ecosystem. So say something like 100 variables are modelled as part of this project. A word about scenarios. Well, we're modelling both climate and socio-economic scenarios. Our climate scenarios come from work in the Chesscape project, so that's 4 different RCP scenarios from 2.6, which is our lowest climate change future, to 8.5, which is our highest. And we have daily weather series, including temperature and rainfall and various other weather data as part of the Chesscape project. We'll also have the socioeconomic scenarios, which here are taken from the UK shared socioeconomic pathways. Those are held in common between various different projects and provide us with a starting data set. They explore a range of futures, from an ecological scenario, sustainability, to one where there's fossil fuel development, and to others in which societal breakdown is a major contributor. Those data sets include things like population futures, growth and decline in some scenarios, land use change, transport use, meat consumption, water abstraction, and many more. And we're extending those scenarios to add in lots of different additional variables as part of this project, particularly those of interest to freshwater quality. Not every socioeconomic scenario can be combined with every climate scenario. So we have a grid shown on the bottom right showing which socioeconomic scenarios and climate change scenarios, RCPs, go together. In this talk, we're just going to use examples from a couple of those scenarios. So SSP1, sustainability, low climate change, and SSP5, high climate change scenarios. So we'll just be using those as examples. To help you get oriented, here's a kind of very broad brush description of the different parts of our modelling framework. We start off with a range of driving data sets that includes the weather, population and land use data that we've mentioned before. These have all been inherited from previous projects, but in some cases extended to the whole of the UK. We're then adding extra data sets represented here by the cup of coffee. That's because we're including things like caffeine consumption rates into the future. Those data sets are all then drawn in by our runoff, discharge and drainage models. Lots of different sub-models responsible for predicting the amount of water and the amount of each different chemical entering the freshwater environment from different sources. So here we've got examples of the wastewater system, farmlands, semi-natural lands like woodland, and indeed direct discharges from industry where relevant. Once all of the chemicals and water reach the freshwater environment, and that includes a groundwater layer as well as surface waters, We then have the freshwater model, which is responsible for routing the chemicals along rivers for chemical processes that happen in the rivers, like photodegradation. And this is also the point where we include abstractions for potable water and other uses. And by the end of the freshwater model, we then have a range of water quality data sets, which are passed over to Cardiff University and to Will and his colleagues to start to predict the health of the ecosystem, including a variety of taxa, which he'll be speaking about later. And so by the end of this project, there'll be water quality data sets and ecosystem data sets all linked together. So today we're talking about the wastewater system, we're talking about the agricultural runoff model, and we'll be talking about the ecosystem modelling. Lots more, of course, to the project, but we won't be talking about those today. So without further ado, we'll now jump into the wastewater treatment part of the model. This is a bespoke model designed for this project, which takes account of the various different methods by which wastewater is produced and what chemicals are associated with it, and takes account of routing into different treatment options that are available in different parts of the country: wastewater treatment works, septic tanks, and potentially direct discharge to rivers in a few areas, but in some of the worst scenarios, we do have that increasing. We're also accounting for the very popular, or perhaps I should say very unpopular, contributions of combined sewer systems. So that includes urban runoff mixing then with the foul water. And ultimately, we'll have wastewater treatment represented together with discharges of untreated wastewater. And so that's why we're including combined sewer systems as part of this model. We also have to ensure that this is a model that scales sensibly into our future scenarios, and of course that it fits inside a limited budget for computer memory and performance, because we can't spend 100% of our effort on sewage modelling. So every model is a simplification of reality that takes a set of assumptions. Here are the big assumptions we're making. We're assuming that all wastewater is treated locally to where it's produced and discharged locally. That means we're going to overestimate discharges in, say, city centres, where sewer networks will pass wastewater further out of the city, but it should be good enough at our 5-kilometre scale for most areas. We're assuming that treatment happens instantly. In practice, of course, it takes a few days, but this is again an assumption we're making to reduce the computational requirements. We're assuming that everything works well all the time and that overflows only occur when it's raining. We're not going to be modelling in this project any maintenance issues or malfeasance. And then we're trying to attempt a minimum parameterization. What is the simplest possible model we can get away with? So we're taking a small set of parameters and trying to link the entire model to these. Those are the production rate of wastewater and the various modelled chemicals as part of the project. The routing fractions, the fractions of that wastewater that ends up in treatment works, septic tanks and rivers. And then each of those different options, particularly the wastewater treatment works, have a finite capacity for treatment and an efficiency, the amount of chemicals that are removed from the water as part of treatment. In principle, all of these can vary over the 100 years of the model runs. They can vary spatially around the country, and of course they will be different in different scenarios. The idea here is to give us enough different parameters that we can vary to represent the different storylines of our scenarios, while not making the sewage model the most complicated thing under the sun. Today, next I'm going to give you a little bit of an indication of how we're parameterizing these models, and particularly looking at the production rate of wastewater, routing to different treatment options, and capacity. So here are some examples. Wastewater production is related to per capita consumption of water, which is shown in the graph here. We have declining per capita consumption from around 200 in the mid-20th century, down to values that we've then taken from the EA, from the water resource management plans, returns from the various water companies from 2005 to 2023, at which point our scenarios then diverge. The current water resource management plan shows a decline over the next 30 years. We're adjusting that for our different scenarios. So in SSP1, our sustainability scenario, per capita consumption declines faster. In SSP5, the fossil fuel future, water use remains relatively high. We're also, of course, taking into account the variable access to wastewater treatment works. This is the UK as a whole, so the fraction of the total population of the UK with access to wastewater treatment works over the 20th century, increasing, shown in brown here, and then reaching a bit of a plateau in recent years, while meanwhile access to direct discharges to rivers decline. This is based on work by Pam Naden in a predecessor project to this work. In this case, we show very little change after 2020 because in both the sustainability and fossil fueled future scenarios, we essentially maintain investment in the wastewater treatment system. That's not the case in all of our scenarios. We're then also taking into account the various guidelines and regulations. So wastewater treatment works capacity. Again, water treatment is happening at a very local level rather than at real water treatment work sites. So we're just assuming that everyone's following the requirements of having flow to full treatment equal to 3 times your dry weather flow and 2 hours of capacity at full flow to deal with rainwater. Again, crude assumptions, but the idea is to be as simple as possible while still giving us reasonable results. So what next from sewage? Well, we're in the midst of integrating the code into our full freshwater model. I'm finishing off the parameterization for some of these future scenarios, particularly the ones that haven't been shown here, the ones that involve societal breakdowns. We'll be validating the results where possible and where we can match existing available data to the model. And then, of course, running the model for our full range of chemicals and future scenarios. That's it for the wastewater system. I'm now going to hand over to Theo to talk about agricultural modelling.
Thank you, Mark. So, just waiting for control. There we go. I'll be talking about agricultural modelling as part of the LTLS-FE. So Rothamsted model arable land using the Rothamsted landscape model. It's a three-tier soil layer model that's previously been used for macronutrients, but for this project, we're also looking at micropollutants. On the right, you can see we model over the 12 nuts regions now, partly because a lot of the data is divided up among these nuts regions, so it makes it easier to spatially disaggregate the data that we're using. We're also including Northern Ireland in greater detail, as Mark mentioned. So that includes livestock specific to Northern Ireland, as well as fertilizer rates, crop rotations, and pesticides. Below, you can see a schematic of how these models are integrated. So today, I'll just be talking about the new and updated submodels, as the RLM is quite a big model in its entirety. So this is a diagram of the classic Rothamsted landscape model, just to give you an idea of how it's working. We've got our 3 soil layers. The soil depth may be adjusted due to erosion or decreases in soil organic carbon and soil density. We have the water moving both downwards and across for runoff. So we have leaching of macronutrients and changes in our macronutrient pools as well. And additionally, we're calculating emissions, so methane, nitrogen, and nitrous oxide emissions from both the land and from livestock as well. So one of the updated models was our erosion model. This was originally developed by Andy Whitmore at Rothamsted, based on Morgan Finley and Psychic models. This was updated by another colleague, Mike Giannotopoulos, based on the 10-year Woburn data from 1988 to 1998. So that looked at daily sediment and daily runoff at the site and calculated the macronutrient fractions in that sediment as well. So this also determines the soil fraction of clay, silt, and sand, and recalculates them after an erosion event, the particulate inorganic loss for carbon, nitrogen, and phosphate in the sediment, and adjust the topsoil depth after an erosion event. As you can see on the right, we've got our simulated with the dotted line and the measured from the woven data as the solid line. So we were quite happy with our validation. If we're ignoring very heavy rainfall events, which may be due to the equipment at Woburn and different soil dynamics during those heavy rainfall events as well. So partially feeding into the, or rather from the erosion metals, the heavy metals model. This was provided to us by Steve Lofts and Ed Tipping at CEH, translated into Fortran for the RLM. It models 5 heavy metals: cadmium, copper, nickel, lead, and zinc, which have been implicated in environmental impact in agriculture. So we calculate different metal species, the labile, non-labile, and dissolved forms. Labile meaning very chemically reactive, fast chemical reactions based on chemical equilibria, and non-labile being slower chemical dynamics, where metal species are adsorbed strongly onto soil particles. So we have inputs of our metals from atmospheric deposition, which is taken from environmental data center values across the UK. So that's spatially distributed. And also fertilizers provide a large input, particularly phosphate fertilizers provide a large input of cadmium, lead, and other heavy metals that we're modeling. Post 1980, the model is being run daily, so these inputs are disaggregated. So we might have smaller amounts of atmospheric deposited metals and larger spikes when a fertilizer is applied. And you can see on the right, the metals can move down through the soil layers out into drainage, into the groundwater, where it's passed on to our ecologists eventually. There's also erosional runoff, so loss of metals from the soil, and crop uptake. Another carrier of our metals is dissolved organic carbon, which is also calculated in the Rothamsted landscape model. So a new submodel of the RLM is the pesticides model. Based on what stakeholders were looking for with our priority pesticides, we're modeling 2 herbicides and a fungicide, so dimethenamide P, benzazone, and boscalid fungicide. Because of their different pest targets, they have different timed releases. So rather than using a date post-sow date, we're using the plant developmental stage. As you can see below, 0 being germination and maximum 2 being for the maturity of the crop. These can take decimal values in the RLM. So for each pesticide crop combination, we will have a lower and upper bound for the DVS values where it can be applied. And in order to determine how often these pesticides get applied and their spatial distribution, we've referred to FERA surveys, which cover the UK, and also have NUTS specific data for pesticide use, spray hectare, and spray weight, and also handily have individual pesticide spray hectare and spray weight data across the UK. Finally, we've updated the livestock submodel. So previously, this was models for Great Britain using the asset livestock scenarios, something like extensive agriculture, intensive, upland, across the 5x5 kilometre grid squares that you can see on the right, and then crossed with livestock unit numbers, we determined livestock rates for each subcell. However, for Northern Ireland, we didn't have this, so we had to refer to agricultural census data of the livestock numbers with our 12 livestock types, and grassland areas additionally within the 11 local government districts of Northern Ireland. And for the Republic of Ireland catchment cells, we've used livestock numbers in the border regions which cover these catchment cells. It's worth noting that that Rothamsted model improved grassland, but not rough grazing. So to get our livestock totals to match, we've included all the livestock in these improved grassland cells. On the right, you can see red being the higher concentration, a high proportion of grid cell containing improved grassland, and blue being much less. So it could be arable or at a portion of semi-natural land as well. As I mentioned, methane emissions calculated, and we're using tier 1 and 2 IPCC methods for that. So to give you an example of how this might play out, looking at some key drivers, if we have take our green future, for example, we suppose a reduction in the use of fertilizers, as a result, a reduction in our phosphate applications across the UK, and then lower heavy metal arable inputs heading into the groundwater and runoff. If we look at our fossil fuel future, because of the climate scenario, we'd have higher average annual temperatures, as well as increased use of pesticides from SSP5. Because of the temperature change, we'd have a higher probability of maize in our rotation, and because of that, a higher probability of dimethenamide, the herbicide application, but additionally a higher median dose due to the increased use of pesticides driver from that scenario. This is just a snapshot. There are many factors affecting the changes in pollutants across the UK, depending on the nuts region, weather, and other scenario drivers. I will pass on to Will to talk about freshwater ecology.
That's great. Thanks, Theo. Okay. Great. So my name is Will Perry, and I'm from the Water Research Institute at Cardiff University. And I work with Ian, also at Cardiff University, and Martin Kelly at Broburn Consultancy. And we're looking at the river ecology element of the LTLS-FE project. And what I'm going to be talking about today is some of the predictions that we're working on. And so really, what does the future hold is what I'm going to be talking about. What's it hold for our river ecology? So this is a nice idealized diagram of what river ecology looks like and what a freshwater ecosystem looks like. And freshwater ecosystems contain a huge amount of diversity. They are the most diverse, or one of the most diverse per unit habitat volume on Earth. So a huge amount of diversity there to be conserved. And there's this really nice statistic here from the WWF in that freshwater ecosystems cover less than 1% of Earth's surface, but they are home to at least 10% of Earth's species. So a really biodiverse habitats. And so understanding freshwater quality in the physical and chemical sense is really important. But what we also want to know is how that interacts with biological systems. And so what we're going to be talking about, or what we're going to be looking about in this project are elements of the biodiversity that we have data for. And these include fish, which are probably my favorite. I'm a little bit biased. We also have macroinvertebrates. So here as shown by the beetle, the crustaceans, annelids, mollusks, that sort of thing. We then also have data from the diatoms, which are microscopic photosynthetic organisms. And then we have data for the larger photosynthetic organisms as well. So the macrophytes, the larger things that you see on the bank of the river, but also in the main channel as well. What do we currently know about the ecological status of the UK's rivers? There was this really nice paper that came out recently that was looking at fish diversity, so the number of species. And things seem to be increasing, if not remaining stable, for in terms of the diversity of fish species in the UK, or at least this was England-based. But we know this isn't the case for all species. They're not all doing well. So this is the Atlantic salmon in Wales and the population levels. And you can see that it's quite a dire picture for the Atlantic salmon, not only in Wales, but around the UK and across its range. So not all species are doing well in terms of fish. And then the macroinvertebrates, we've seen really nice increases in diversity of macroinvertebrates through the 80s and 90s. But what we're seeing now is that this increase in diversity is starting to slow down, which is a bit of a worrying trend. So we saw great increases in water quality that have helped increase the diversity of macroinvertebrates, but yeah, it's now plateauing. So what data sets are we using? So we're using data sets from the Environment Agency for diatoms, fish, invertebrates, and macrophytes. We then also have some data for Northern Ireland for the diatoms and macrophytes, although unfortunately not fish and invertebrates. For Scotland, we've got diatoms, fish, and invertebrates. And then in Wales, we have the same as in England, the whole suite of those organisms. So between all of these taxa, we do have complete UK coverage. Although if anyone can help us plug some of these gaps, would be very grateful. Yeah, for that. And just to go through how this data is collected, so we'll be using electrofishing data for the fish. So this is where the environment agencies will go out to a river or a stream. They'll pass a current through that water and stun the fish. Those fish then float to the top. You find out what species of fish they are, and you enumerate them. And for the macroinvertebrates, we're using the 3-minute kicknet samples collected by the agencies. So this is pretty, does what it says on the tin. You go into a river, you kick about, and you have a net, and all of the things that you suspend in that water column go downstream and are collected in that net. You then look at what species are there and just how many of them there are. Diatoms, microscopic, so you've got to use light microscopy and more recently metabarcoding to identify what species are there and their relative abundance. We also have macrophytes, which we're using percentage cover surveys. And that's the suite of data sets that we have from the agencies. Okay, so we've come up with some preliminary predictions based on temperature predictions, as well as some preliminary cetirizine predictions from the broader LTLS-FE team. And these are based on the RCP 2.6 and SSP1 that Mark was talking about, so that particular scenario. And cetirizine is an antihistamine, and so is sort of like a wastewater signal. So between these two, these are some early predictions, that preliminary predictions that we've come out with, and we've used machine learning to understand how changes in these two parameters might affect biodiversity. We've done this for fish. It's the fish results that I'll be showing today. Again, it's my bias here. And so this is for fish species richness that we have here. So we've got different time steps going through the decades along the top. So number of species, the higher they are, it's sort of like a yellowish color. The lower it is, it's a darker blue. Then we have fish species richness change here at the bottom. So the red areas are places that we're predicting there may be decreases in fish species richness, and the bluer areas are areas where we might see increases. And that comparison is between our 2018 prediction, our 2080 prediction compared with the period 2008 to 2013. We also have done some preliminary predictions for Atlantic salmon as well. And again, you've got the time steps along the decades at the top, and then you have that difference between 2080 and 2008 to 2013 at the bottom there, with the reds showing places where they're not going to be doing so well, and the blues showing where they are going to be doing well. And as you can see, there's a lot of red there, and that sort of correlates with what we know and the way that things are going for the Atlantic salmon. So moving forward, we're going to integrate more variables on water quality and beyond as well, so things like land use, when these data sets are generated from the broader team, things that Theo and Mark have just been discussing. We're going to investigate more mechanistic ways of modeling the interaction between ecology and water quality. So not just that machine learning approach, we're hoping to also look at more mechanistic ways for predicting how that biodiversity is going to change. We're going to work on getting these predictive outputs on the web tool so people can have a play around with them. And then we're also going to explore how other taxa and metrics are going to change under future scenarios. So things like our macroinvertebrates, diatoms, macrophytes, things like traits, phylogeny, but also some of these metrics that are used by the agencies, such as the RMNI, ASPT, and TDI scores. And with that, I'll pass back over to Mark.
Thanks. Took me a moment to get my microphone back on. Well, thank you all. So very briefly in conclusion, we've been talking about the LTLS-FE project, where we're looking at modelling water quality and ecosystem health from 1980 to 2080, taking into account these various climate and socioeconomic scenarios. We've got a big model taking into account lots of different sources of pollutants, lots of different approaches to treating them and modelling the chemical processes that take place. And we've given you a bit of an introduction to 3 of those sub-models. At the moment, we're in the midst of producing our final driving data sets, particularly for those future periods, validating and testing the model. And also, we've recently finished a series of stakeholder interviews about which outputs will be most useful, how can they best be displayed, what kinds of questions would you like to be answered. Thank you all to anybody who's taken part in that. If you're on the call today, we're now collating the results, and we're very excited about getting these outputs ready for you. At that point, I think it's time for us to wrap up. And so I think we now have a bit of a Q&A.